nice place.
Oh, there we go.
Very nice.
Thank you all for coming.
Yeah, to take all these pictures.
I'm John. Appreciate you being here. We have our meetings an hour early today because of the celebration of life. That's going to be starting at 2 o'clock. We want to make sure they're absolutely done well before then. So thank you for coming at an earlier time than planned. So why don't we go ahead and get started? I view this presentation as you've come to the right place for a journey through space. And once you leave Earth, GPS doesn't work. So, make sure you got your space suits on, buckle your seat belts, because it's going to be a quick presentation through a fair amount of currently visible constellations in the south and eastern skies, and a little bit straight up as well. So let's go ahead and get started. First of all, a picture of the moon. Now, you've probably seen hundreds of these pictures of the moons. What makes this one so different? I'm kicking myself because after we took this picture through the telescope, we went ahead and did other images through other things and lost the opportunity to take a cell phone picture of where this was taken. Turns out the moon from the observatory was positioned in such a way that it shone through the space between the lamppost and the lamp, the street lamp. So this is a picture taken through the street lamp. The lamppost is here, the street lamp is here. And this is that space right in between the lamppost and the street lamp. It's just amazing that we were able to catch the moon right then. And we were curious to see whether the rings of Saturn were starting to show up, because they've been edge on for the last 8 months or so, or a little longer. So we took a real quick snapshot, a few milliseconds, and lo and behold, we actually got the moon Titan in there as well. It's right there. Little kind of dim little dot right there. I don't know if you can see it, but it's right there.
Can see
So
the
that was,
rings.
I'm sorry?
Can see the rings.
Yeah, and you can see that the rings are starting to become a little more visible.
Yeah, nice.
Okay, thought we ought to have a review of magnitude, because it's such a difficult concept to understand. What makes this chart easy to use is that when we are looking at differences in magnitude, for example, we're going to be looking at Corona Borealis constellation here pretty soon, and we've been watching T Corona Borealis because it's supposed to go nova anytime. It's a recurring nova. It goes nova. In other words, it blasts its outer atmosphere every 80 years, and it last did that in 1946. So between now and hopefully before 2026, it'll go nova. But we want to wait till it gets back into the northern hemisphere. Pretty soon it's going to be below our view of sight. We won't see it unless early in the morning. Well, anyway, right now, Epsilon Corona, right here, ECRB, shines at a 4.28 magnitude. TCRB shines at 10.3. That's a difference of 6 magnitude. So what does that mean? If you go over to the chart, you go over to 6, that's 251 times. So what this says is that Epsilon Corona is shining at 250 times brighter than T Corona, and you'll see that in a slide shortly. The other thing is, you go to really dim stars, barely able to see even with a telescope, maybe you can't see with a telescope. We've got one we're going to look at that's 19th magnitude. So you go to the chart, take 10 magnitude, multiply it with 9 magnitude, and we see that 4,000 times 10,000 is 40 million, times dimmer than the base star of 0 magnitude Vega. Okay? Vega is, I'll show it to you in a little while, is a 0 magnitude star, and it is the baseline for magnitude and color index. Okay? So each increase in magnitude is 2.5 times. So a first magnitude star is 2.5 times dimmer than a 0 magnitude star. Okay? That's how that works. Also, we're going to be looking at the Milky Way galaxy, at least an arm of the Milky Way galaxy. You'll see that pretty soon in a moment. So I found an illustration of what our Milky Way galaxy looks like if we were above it looking down. And we can see that it is a barred spiral. We are located here where it says Sun. We are on the Orion arm. The Orion arm is not really a standalone arm by itself. You can see that it merges with the Perseus arm right here. It merges here and merges over here. So it's not a full arm in and of itself. Also, the spiral arms are the major regions of star formation in spiral galaxies. And this is where we'll find most of the major nebulae in the spiral arms. Okay? All right, so if you were to go outside tonight and if the sky was clear and it was dark enough, you'd be able to see some of these stars. Unfortunately, around here, we cannot see the Milky Way galaxy. I remember as a kid growing up in greater Los Angeles area, we could go out at night and see the Milky Way galaxy. In LA, are you kidding? Anyway, you can see the arm of this Milky Way galaxy right here. This is the Sagittarius arm. Go back one slide. That's this arm right here. And so we're looking at it this way after sunset. Okay? So we see this arm, and we'll be traveling through here. And the closer we get to the end of Sagittarius, the galactic center is, if I can hold this steady enough, right there. That's the center of our galaxy. Okay? And like on any trip, especially if you don't have GPS, and when we're traveling in space, we don't have GPS. We need a map. So, got a map. Right there. So we're going to start using the Big Dipper. Usually use the Big Dipper, the pointer stars to find the North Star right there. Use the pointer stars. However, in this trip we're going to start here and we're going to make a line right through the handle, straight line over to Corona Borealis. That's this constellation right here. It's called the Northern Crown. And Epsilon, but it just showed you a little ago, was right here at the end of that arrow, right there. And then T Corona is located right here, right about there. And remember, T Corona, what did we say? 6 magnitude difference, so 251 times dimmer. Then we're going to travel around Hercules, revisit Lyra for just a little bit, and then go on over to Cygnus. View a number of things in Cygnus, travel down the spiral arm to Ophiuchus, interesting star over there, and then we'll swing out back around to the galactic center, and then take a straight shot over to Aquarius right here. We'll end right here. And I showed you Saturn already. So the big trip around the sky, we're going to see supernovae, we're going to see very large stars, and we're going to see very, very cool red dwarfs as well. And we hope to see and look into the question of, can there be life in a nearby miniature solar system that was only recently discovered? And we'll wind up there, the treasure, okay? So we'll start off with Corona Borealis. This is a review. This is the normal traditional view right here. North is up there. I had to turn it in order to match the position of Corona Borealis with where we are currently. So by rotating that, I was able to put it in the same position as, where to go, right here, right there. All right, so it's in the same view. And you can see that right here. All right, there's Epsilon right here, and there's T Corona Borealis right there. That empty space, we've got a circle around it. So what's going on? Like I said, it's a recurring nova. It's one of only a few, very rare. There are about a dozen recurring nova in our galaxy that recur regularly in a less than 100-year cycle. T Corona is about an 80-year cycle. So there's only about a dozen that we know of in our galaxy. So we're waiting with bated breath for this thing to blow its atmosphere off, and hydrogen. It gets the hydrogen from its companion star. Because of the gravity, it accretes in a disk around the white dwarf star. Then every 80 years it blows off that hydrogen into a very super huge thermonuclear explosion. And it does not harm the star, the white star at all. It just blows it off in the sky. We could see it from here. So here's a collage of images. We've been taking pictures about every night, waiting for this thing to go. So this is what it looked like back in March from this angle. So this was in the east, just above the treetops, and we took this picture. This is facing east. So Epsilon is here at the top of the screen. T Corona is here, facing right side up. So the scope was, because the Earth was rotated, the scope was kind of moved that way. As it came around later in the summer and to current, we can see in August, it had moved around. Now we were able to capture Epsilon and T Corona again in September, a month later, same thing. And then on the 20th, which is that Monday night, we took another picture. Actually, I think took one a couple of nights ago as well. And it has not gone nova yet. We're still waiting. Okay, now we're going to go from the Corona Borealis up to Constellation Lyra. And again, I had to turn it on its side a little bit in order to match our view. So we're going to be just a real quick look at Vega, and then there's a carbon star that I want to show you that's right about here. Okay? Vega. What's so interesting about Vega? Remember, I mentioned Vega was a zero magnitude star. It's the baseline from which we measure magnitude and the color index. So Vega is a blue supergiant star. It is actually spinning so fast. It's an egg shape. Can you see an egg shape? Does that look oval to you? It should be horizontal. Actually, in this shot, I think they have it turned the other way.
It's oval.
Oh, no, okay. Yeah, I can see it on my screen. It's oval. All right, it doesn't look so oval there. So the reason why it's oval is because it's spinning so fast. This star is only 25 light years away. It's over twice a solar mass. It's 2.5 times the radius of our own sun. Its rotational velocity, it's rotating at 147 miles per second. And it's very close to its part where it could come apart, fly apart, but it hasn't. Right? There's enough gravity keeping it maintained at that level. Okay, and it will become the pole star about the year 13,700. It was the pole star in the year 12,000 BC, but because of the Earth's wobble, it's what they call precession. It actually traces a circle around the night sky as it precesses around. Just like, I remember when I was a kid, I had a top. I think most everyone, when we were kids, we probably had tops. The younger folks probably don't know what that is. You spin a top, after a while, it starts to wobble. Or maybe it's even a wobble when you spin it. So that's what the Earth is doing, it's wobbling. So what's happening, let's go back to our other slide. Here's our current North Star right here, Polaris. Year 13,700, so 16,000 years from now, Vega is going to become the North Star. In between, and I'm getting a little ahead of myself, but since I'm here, I'll show it to you. Deneb, which is the bright star in the constellation Cygnus, will become the North Star in the year about the year 9800. So what's going on is the Earth, if you were able to trace a line, a circle, is forming a circle around like this, going around Deneb, and around Vega, and coming back around. So we can actually trace out the Earth's wobble in the sky. Okay. Does that make sense?
It's a very slow wobble.
It better be. I don't want it wobbling any more than I do. All right. So we took a couple shots of Vega. This one was at 250 milliseconds. That was a 4-second exposure. And you can see that it's not exactly circular. Right? If I could expand this out, this image right here, I've done it. I'm not going to do it now because I don't want to take up the time. I've got too much traveling to do. But if I could expand this screen out, I can show you the egg shape. You can actually see it in the image. You can see it somewhat in this one, this slightly overexposed image. You can see that that's not exactly round. I was surprised to see this. I was not expecting it. I was expecting a round. I knew Vega was oblong, that its poles are actually closer to the center of the star than the equator is. But I was not expecting to see it in our little tiny 6-inch telescope. That telescope still amazes me. The things that it images, it's beyond. It's just wow. Let's move along. This has to be a quick trip. Okay, I mentioned carbon star, T Lyra. Carbon stars are very rare, very rare. They're red stars. Most red giant stars contain more oxygen than they do carbon. Some cool stars feature a rare condition in which the carbon has become more abundant than the oxygen, and they're called carbon stars. It takes 2 helium atoms and a 3rd helium atom to form carbon. So hydrogen fusion into helium. When helium starts fusing, it creates the higher elements, carbon and oxygen and neon, etc. No stars are darker red than carbon stars, and T Lyrae is a stellar ruby among carbon stars. And you can see how red that is right here in our image with our telescope. It's located, as I mentioned, right there. There's Vega. T Lyrae is right there. So why is this a carbon star? So as fusion continues, the core gases circulate upward, carrying the byproducts of fusion, in this case carbon and oxygen, to the star's outer layers. When circumstances are right, carbon compounds proliferate in a circumstellar shell material, forming a soot layer that gives a carbon star its particular red and red-orange color. Soot, just like a buildup inside a fireplace or a chimney. Okay. And we can see this on the periodic chart. Hydrogen fuses together, makes helium. Fuses those together and another helium atom, you'll make carbon, and then oxygen. So every even element, every other element. So then carbon, another helium atom makes oxygen, another helium atom makes neon, all the way down to you get to iron. And the structure in iron is so tight that there's no more fusion after iron. I put this up here and I just remembered my high school chemistry class. I'm going, oh wow. I hadn't seen that chart for a long time. Okay, same thing now with Cygnus. Had to turn Cygnus on its side because in that image I showed you, from our view currently, at today's date, it's lying kind of more on its side. Deneb is the brightest star, as I mentioned. It's the tail feather of the star. And here's the belly and the neck and the beak. It's a swan, okay? The wings come out the side. Right. So Deneb is we'd call it's a variable star. It's an Alpha Cygni variable. It's a blue-white supergiant. I mentioned we're going to be talking about supergiant stars and what have you, black holes and what have you. It's approximately 1,400 to 1,500 years old.
Downstairs. Yeah.
It's a prototype of class of variable stars known as, I mentioned, the Alpha Cygni variables. Its brightness fluctuates slightly as a result of non-radial fluctuations of the star's surface, meaning that some parts of the stellar surface are contracting while others are simultaneously expanding. The pulsations can appear irregular because there are multiple pulsation periods. The nature of the non-radial fluctuations in these stars is not fully understood. We just know that they happen. Yet while these fluctuations make it difficult to obtain accurate distance measurements and mass and that kind of thing, Deneb is nevertheless the most distant star that shines at first magnitude. So it is a 1.25 magnitude star. It's roughly 200 times the size of our sun, 20 times solar mass. So it will go out as a black hole, a supernova, excuse me. Surface temperature is 8,500 degrees Kelvin, which is 15,000 degrees Fahrenheit. Our sun shines at just under 10,000 degrees Fahrenheit. And its luminosity is 100,000 times brighter than our sun. So it is the largest blue-white stars known, and one of the largest and one of the most luminous stars known. It has stopped fusing hydrogen in its core and is expected to go out as a supernova within the next few million years. So I put the two side by side so we can compare them. This is Deneb, we just looked at. This is Vega. They're both blue-white supergiants. Vega is 2 times the mass of our sun. Deneb is 20 times. Deneb is 1,500 light years away. Vega is 25 light years. Vega's luminosity is 40 times. Deneb's is 100,000 times. Deneb is 1.25 magnitude, while Vega is 0 magnitude. And I mentioned before, Deneb is expected to become a pole star around the year 9800, and then Vega's turn will be around 13700. Someone was talking with me about why they thought that stars are brighter than other stars or dimmer than other stars. And the person thought it had all to do with distance. In this case, it has a lot to do with distance, as you can see, because Deneb is the bigger, brighter star, but yet from where we are, it's not quite as bright as Vega. So distance plays a big part in this, but not always true. need to take a look at composition as well. And we'll see that as we go on. Okay, where I said was the belly of the swan, we'll find this star, Gamma Cygni. What's interesting about Gamma Cygni is that it's a young blue supergiant star, much like we've been looking at, about 12 million years old, and it's surrounded by the diffuse emission nebula right here. So this nebula is an emission nebula, so it emits its own light. It's not a reflection nebula where it's getting light from some other source. And also in the same image you can see the crescent nebula right here, which we'll take a look at in a moment as well. All right. '61 Cygni. This is a really interesting double star. There are actually two dwarf stars. It's notable because it's so close to us and we can visualize its proper motion. In other words, we can actually trace its movement against the background stars over some period of time. P Cygni is interesting because it is a hypergiant luminous star, a blue variable. Its luminous blue variables are very rare and only found in regions of intense star formation. They're usually very short-lived. Because of their enormous mass and energy, they exhaust their nuclear fuel pretty quickly and erupt into supernova after only a few million years. And it is one of the most luminous stars ever discovered in our Milky Way galaxy. It's nova-like in its appearance, and even a hypergiant so massive barely holding itself together, much like Vega. It is a beacon of luminosity, and it loses mass steadily at some 300 million times the rate at which our sun loses its mass via solar wind. It will one day erupt into a supernova and become a black hole. The North American Nebula, again we're still in Cygnus, traveling down the neck of Cygnus. This is large. It's 120 by 100 arc minutes. In other words, it's each 60 arc minutes is 1 degree. So this is 2 degrees by just a little less than 2 degrees. So it's fairly large. The full moon is about 29 arc minutes in diameter when we look at the full moon. So it just gives it a little bit of perspective. This is the North American Nebula right here. You can see California over here, and there's Mexico, Central America. And this is right next to it, about 1,500 light years away. It's the Pelican Nebula, and you can kind of sort of see a mouth right here. This is an area of intense hydrogen region. You can see all this reddish color right here. It's burning hydrogen, red. Oxygen burns blue. And then this is the Pelican Nebula through our telescope. You can see it right here. There's the mouth, and then here's the rest of the pelican. Here's the Crescent Nebula I mentioned earlier. This was taken, I believe, by Hubble. So it's really pretty. It's got a lot of blue in there, some reds. I said that oxygen burns blue, so got a lot of oxygen burning here. and it is an X-ray emitting source. This central star right here is called a Wolf-Rayet star. They're very rare, and they're very, very large and powerful, very luminous. The Crescent Nebula itself is 7.4 magnitude, has a diameter of 26 light years. Light years, as you might recall, is the distance light travels in a year, roughly 6 trillion miles. And it is 5,000 light years from Earth. The central Wolf-Rayet star diameter is 5 times the size of our sun. Mass is 21 times our sun's mass. Its luminosity is 60 times, and its temperature is 10 times our sun's temperature. So they are extremely luminous, and they're even found a galaxy that has so many of these, they've named it a Wolf-Rayet galaxy. They're very old. Very old in the sense that they have found them in distant areas and galaxies. But their lifetimes are not all that long ago because they burn so much that they burn fairly quickly. What causes this shape right here is because it was blown off by when it entered a red supergiant phase, and at the time it ejected about 5 solar masses worth of material that was still moving away at the rate of 50 miles per second. But the solar wind that it emitted by the Wolf-Rayet in its current state moves much faster than that, around 1,000 miles per second. So when this wind crashes into the older, slower moving material, it effectively bounces off, creating an inward moving shock wave that heats the stellar wind to X-ray transmitting temperatures, giving the nebula its glow. And as you can see, it is emitting oxygen and hydrogen in both red and blue colors. And this is what it looks like in our telescope. Only exposed for 1,200 seconds, 20 minutes. Moving along, the Veil Nebula still in Cygnus, also known as the Witch's Broom, at least the western Veil portion of the Veil Nebula. This is an image from Hubble, so it has the advantage of being a big telescope and it's out in space, so it doesn't have to deal with atmosphere. I like this image because it's just so beautiful, all these colors and things going on inside here. Looks kind of like a veil. This is an image of the Western Veil Nebula through our telescope using a nebula filter. So it accentuates the reds and blues, the hydrogen and the oxygen. This next one is the Eastern Veil Nebula taken with a clear filter. Okay, now we're getting into some of the really juicy stuff. Black holes. Black holes. What you're looking at in that circle, did I put that circle there around that star? Is you're looking at a black hole. But you can't see a black hole by definition. You can't see it. You can't, not in visible light. You can see it in X-ray light, radio wave, but not in invisible light. So you look for black holes that have companions. And in this particular black hole, which is the first one discovered, Cygnus X1, in 1964, they sent a rocket up, took pictures. It took them about 10 years to finally decide, hey, wait a minute, this truly is a black hole. They've done a lot of investigating and stuff. They finally realized that it must be a black hole, and it's small. The radius is only the radius for the black hole itself is only about 25 miles, so diameter would be just over 50 miles. The companion star, though, is a supergiant, another blue supergiant star that shines at magnitude 9. It's 40 times solar mass. Its radius is 15 to 17 times that of the sun. And it's 7,200 light years away from us. Most recently updated that number in 2021. And it's very luminous, at 300,000 times the sun's brightness. And its temperature is 53,000 degrees Fahrenheit. And it's losing atmosphere to the black hole. We find it by first looking for Eta Cygni. Eta Cygni is in Cygnus, and it's easy to find. It's in the middle of the neck of Cygnus. And it's a magnitude 4, so it's fairly easy to find. A nice little orange giant star. And then we use a star map. When I first looked at this, I'm going, okay, Eta Cygni, see that easily enough, but where is the companion to the black hole? With all these stars in around, it's like, how do you find it? So, I have a map. So I did, is I put the map out there, and it showed me, somebody put this map together, showed me how to find star hopping, how to get to the black hole. So what I did is I did that. Now, I'm not able to rotate this currently because I have this in presentation mode. I'd have to take it out and put it in my own, not out of in presentation mode in order to rotate this image. But if I rotate this image about 120 degrees, these stars line up. Eta Cygni is right here. Imagine this is being rotated, so then HIP is right here. TYC is up here. And these two little guys are right here. And this one is the companion star to the black hole. So I circled it right there so we can see it easily. But until I got this map and rotated so it's in the same view as this, it was just looking at a whole bunch of stars. Okay, so Cygnus X1. The system, Cygnus X1 and its companion star, orbit at about a distance of just under 19 million miles. Our Mercury, the first planet in our solar system, Mercury, has an average orbital distance from the sun of about 35 million miles. It varies from 29 million to 42 million, but average about 35 million miles. So, this supergiant star and the black hole are orbiting within half the distance of the Mercury from the sun. So it's incredibly close, incredibly close. And they take only 5.6 of our days to complete an orbit. So gas flows away from the companion star toward the black hole, forms a wide, flat accretion disk, then encircles the black hole. Friction heats the gas to 1 billion degrees or more, causing it to emit a torrent of X-rays into a pair of jets that take some of the energy generated by the material away into space. The black hole's strong gravitational field shifts the energy emitted by this gas to longer and longer wavelengths. Now remember, with the gas material coming off the blue supergiant is blue. As it gets close to the black hole, it goes through a slight visible light wavelength, and then it approaches the event horizon of the black hole. It becomes, a redshift becomes so great that the material disappears from view into the black hole. So the event horizon is that edge of the black hole from which nothing is going to escape. You want to, if you ever get close to a black hole, you want to make sure you get away from it before you get close to the event horizon, if you can. As things approach the event horizon, the gravitational field stretches everything that approaches it. So it even just stretches the wavelengths of the light. Cygnus X1 and the supergiant star do not eclipse each other from our perspective. It is one of the most rapidly rotating black holes yet discovered. It spins at about 800 times per second. Now remember, this thing is just over 50 miles wide and spinning at 800 times per second, close to the speed of light. It's traveling so fast, it's spinning so fast. Just as perspective, a hummingbird's wings flap at a rate of 70 to 80 times per second. 70 to 80 times per second for a hummingbird. And a hummingbird is small. This black hole is 50 miles in diameter, just over. And it's spinning at nearly the rate of the speed of light. 100 times faster than a hummingbird's wings can flap. Next slide, I'll show you what an image looks like, what we were just talking about. We can see the material coming off the blue supergiant. It goes through as the light from the material gets stretched into longer wavelengths. It goes through a period of visible light where we see that little white dot, star, before it continues to stretch into a red end of the spectrum. And the energy radiates off into jets, as we had mentioned. Now we're going to continue traveling down. We're going to leave Cygnus. We're going to just do a quick visit to Ophiuchus. That's the serpent bearer. The reason why I want to go here is because I'm going to be going to go from the big and the very big and the very heavy gravitational to small, very small red dwarfs. Okay? And there is a red dwarf
right back here. Right back here with this camera. Right here. Right up there.
It's called Barnard star. This is the second closest star to us. Alpha Centauri star system, triple star system, is the closest star system to us, but we don't see that in the northern hemisphere. It's visible more in the southern hemisphere. But Barnard star we can see in the northern hemisphere, and it is approaching us. You can see the arm, the Sagittarius arm of the Milky Way galaxy going through here. And as I mentioned, the galactic center is right about here. We just went through, we visited Vega, went back through to Deneb over here, shot down through here. Now we're coming through Cygnus. Now we're coming over to Ophiuchus, and a quick visit to Barnard star. There it is, through our telescope. It is a red dwarf, which means it's not very visible. The distance is just about 6 light years to its magnitude 9.5. Remember T Corona we talked about earlier was a 10.3 right now. So very faint. Its mass is about 17 times solar, 17%, excuse me, of solar. And its diameter is only about 15% of solar. Its luminosity is 1/2500th that of our sun. Whereas we looked at one of the others, like 300,000 times, that big super giant companion star to the black hole, was 300,000 times solar. This star is 1/2500th luminous relative to our sun. Its proper motion is 10 minutes per year. It's most of any star. It has 4 exoplanets that we've discovered, none of which are in a habitable zone. The planets are located too close to the star to be habitable. And we can track the motion, the proper motion a Barnard star against background stars. About once every year, if you were to take images, once every year, you could actually see it moving against the background. So it's approaching us. At a rate of 68 miles per second, and it'll make its closest approach, it'll be at 3.9 light years. So it'll gain about 2 light years as it comes close to us, but that's as close as it's going to get. Okay, back to here, just to kind of visit where we were and where we're going. Okay, so we've just visited Barnard Star. Now we're going to go over to the galactic center into Sagittarius. Okay, and then from there we'll shoot down to Aquarius. Okay, so this is Sagittarius. It's distinguished because it has a teapot shape. There's a spout, there's a lid, there's a handle. Okay. If you follow a line from this star to the handle here, you would point to the galactic center. Okay. In this image, this star is right here. This star at the top is right here. This star is this one. This star is this one. So you can see the teapot shape. Here's the lid, here's the teapot. And then here is the spout. This star right here is this right here. And then this, the imaginary line from here through the spout, puts us right into the galactic center, right there. Now I wish I had more time. If I did, I would have loved to present this. Julie just brought me an image of the Trifid Nebula. I don't think I had a chance to put it in here. But at any rate, beautiful image that she showed at the club fair. So Dick has taken pictures of all these. He's got the Eagle Nebula, the Omega, the small Sagittarius star cloud, the Trifid, and Lagoon Nebula. He's got all those that he's taken. So I'll have to show them at another time. This large stellar Sagittarius star cloud is right here, right next to the galactic center. And here's that, what's called the small Sagittarius star cloud. So millions and millions of stars in this view. It's 10,000 light years from Earth, a magnitude of 4.6, 600 light years wide, and it is in the Sagittarius arm of our galaxy. If you recall the image of the galaxy that I showed from looking down, it's the arm that's just inside our arm. Okay, so we're looking towards the center of the galaxy. It's 220 million years old, and its radius is 300 light years. So there's millions of stars are found along the plane of the Milky Way. Okay? And you can see it's a lot of stars. Oh, I did put the Trifid Nebula in here. I think this image looked better on Julie's big screen that she had at the club fair today. These colors really popped on that screen. But you can see all the stars. Again, we're looking towards the galactic center. A lot of stars. But that was just a stunning image, I thought. Okay, so what's going on at the galactic center? Well, we know that there's a black hole there. It's way bigger than the black hole that we showed in Cygnus X1. The first black hole that we were able to confirm was a black hole. This black hole is a supermassive black hole. The distance is 27,000 light years from us. It is 4 million times the mass of our sun, and its diameter is 35 million miles. Now remember, Cygnus X1 was only 50 miles, 52 miles in diameter, 50 miles. 52. This is 35 million miles in diameter. Okay? And this was a composite image of various different wavelengths, because you can't see it in visible light. Radio light, X-rays, and gamma ray light. Okay, so can life exist on another planet? Have we found potential life at a nearby miniature solar system? That's the question that people are asking. Red dwarfs. So this is another red dwarf, TRAPPIST-1. Its mass is red dwarfs in general have masses between 7 to 50% of our sun, so much smaller. Their temperature is around 2,500 to 4,000 degrees Kelvin. Our sun's temperature is just under 6,000 degrees Kelvin, 5775, which translates to 9,950 degrees Fahrenheit. And not very luminous at all, as you can see. A maximum 0.8 solar luminosity. But they're very long-lived. They live to be billions and trillions of years old. And the lifespan is due to convection. Helium is generated from the burning of hydrogen in its core, as we talked about earlier. It's carried to the outlaters. It cools on the surface and then slowly sinks back to be reheated again, and the process continues on. Because of its low mass, this convection is how it achieves a state of balance or equilibrium. Red dwarfs will not become red giants, as there's no chance for expansion. They're fully convective and will completely burn their fuel, as opposed to other stars that do not have to burn all their fuel before they start burning other chemicals, elements, helium and others, as I mentioned before, neon and carbon and oxygen. Red dwarfs will not do that. Last month, Dr. Bishop put the Drake equation up. She's from the SETI Institute, the Search for Extraterrestrial Intelligence. And I was fascinated by this. So what we're looking at is an equation that we're trying to figure out what we need to consider in order to determine whether there's life on another solar system. So you need to know what's the average rate of star formation per year in our galaxy, the fraction of those stars that have planetary systems. You gotta make sure it's got a planetary system first, or second. The average number of planets that could potentially support life for that star and its planets, the fraction of those planets where life actually develops, and the fraction of planets with life where intelligent life evolves, etc. So this next star that I'm going to show you, this solar system, we are right here. We've confirmed down to this level the average number of planets that could potentially support life for this particular star. That star is called TRAPPIST-1. TRAPPIST meaning Transiting Planets and Planetesimals Small Telescope. So these two small telescopes are 24 inches in diameter, were designed specifically to search for life in other solar systems. So TRAPPIST-1 is a cool red dwarf located in Aquarius. It was discovered by Caltech astronomers late in 1999, was reported in 2000. The star hosts 7 known extrasolar planets, in other words, exoplanets, discovered in 2016 and 2017. Up to 4 of these planets orbit the star's habitable zone, where temperatures allow for the existence of liquid water on the surface and may be hospitable to life. With an effective temperature of 2,566 degrees Kelvin, TRAPPIST-1 is the coolest known star with confirmed exoplanets. And it's just off the ecliptic. The ecliptic is that path, the imaginary path that the sun traces across the sky as it goes through the sky there throughout the year. All right, so TRAPPIST-1 is 40 light years away from us. It's about 10% the mass of our sun. It's extremely small. It's about 12% the radius of our sun. Again, it's about 4,000 degrees Fahrenheit. Its age, it's already 7.6 billion years old. Our sun is about what, 4.5, something like that? So this thing is like 3 billion years older than our sun. It rotates 3.3 days to make one rotation. Its rotation velocity is 3.5 miles per second, so it's a fairly quick rotating. Magnitude 19, it resides close to the ecliptic. It's only 20% larger than Jupiter. Jupiter is 88,000 miles in diameter. The TRAPPIST-1 is about 105 miles in diameter. So pretty small. So these two telescopes, one's in Chile and one's in Morocco, so that way they can get a 3D image, you might say. Like we have 2 eyes, you know? We can get, by having a telescope on one side of the planet and one on the other side of the planet, we can look deeper into the space. So this is a size comparison, and I'm almost done. Real quick check of the time. Good, we'll make it. All right. Okay, so here's our sun right here for comparison. Here's the planet Jupiter, and here's TRAPPIST-1 for size comparison. So it's red, and it's just slightly bigger than Jupiter. And these sizes are for comparison, so they are relative. These are the 4 biggest moons of Jupiter, 4 of the biggest moons of Jupiter, for size comparison. These are size comparison of Mercury, Venus, Earth, and Mars, so you get an idea of their sizes. Notice the 7 moons of TRAPPIST-1. They're all roughly the same size, about the same size as Earth. Some a little bit bigger, some a little bit smaller, but roughly the same size as Earth. But look at the size of TRAPPIST-1 versus the size of our sun. So for somehow, this little star's got all these 7 planets that it's keeping in orbit, and guess what? Those planets are about the size of Earth. So they're not really small planets. I mean, if we think Earth is big. Okay, this is a view showing a few different things. It has our planets, Mercury, Venus, Earth, our moon, and Mars. It shows area of habitability and relative size. So we can see that the relative size of these planets are about the same size of Earth, give or take. Colder on this side, warmer on that side. Because this is a red dwarf, it emits more light in the infrared part of the spectrum than it does in the visible part. And infrared, as I'm sure you know, means heat. If you put your hand in front of like an infrared heat lamp, your hand gets warm. You can feel the heat coming off the lamp. So the habitable zone for TRAPPIST is further out in its solar system than the habitable zone for our solar system. And our solar system, our habitable zone goes from just past Venus to include Mars. So Earth and Mars are within our solar system habitable zones. For TRAPPIST-1 system, some say D, E, and F, planets D, E, and F, they don't have names yet, they're just alphabet numbers. Or it could be E, F, and G are within the habitable zone. And I believe they detected some water particles on, I'm not sure which one after that. It mentions the Goldilocks zone. That's another name for the habitable zone. So the idea here is that The Hubble Space Telescope revealed the first indication of possible water content of the planet, of TRAPPIST-1 planets. An international team of astronomers found that the outer planets in TRAPPIST-1 system may still contain significant amounts of water, including the 3 planets in what you call the Goldilocks zone, or the inhabitable zone. So these 3, or it could be these 3, most likely it's these 3, that still contain significant amounts of water. And they're able to do this not with visible, but through spectrum and that kind of thing. Spectroscopy. Okay, if you were to put the TRAPPIST-1 solar system next to our solar system, and you expand it out 25 times so you can see what this solar system, how it would look if expanded out 25 times versus our solar system. First of all, thing to notice is that the entire solar system of TRAPPIST-1 and its planets occupy a space about 1/3 or less of the orbit of Mercury. The whole solar system could fit well within the space of the orbit of Mercury. The next thing you notice is as I mentioned, the size of the planets versus the size of our planets. And the habitable zone, or the Goldilocks zone, is the green areas. Okay, right here. The astronomers have calculated that temperature is just right for liquid water to pool on the surface on an Earth-like world within the habitable zone. So these 3 or 4 are good candidates for life. So the question continues, could there be life on a nearby? This thing's only 40 light years away, so it's like on our doorstep. And I don't know how this got in there, but this, I think I already showed this to you. Yeah. And that's the end of my presentation, and I think I wound up just on time. 1:35 right now, right on time.